In this lecture, we will discuss about hydrogenic atoms. Now, what are hydrogenic atoms? Let us consider a 1 electron atom having atomic number Z. So, 1 electron atom, that means there will be 1 electron. We know that for Z equal to 1, that is for the hydrogen atom. So, for hydrogen atom, Z is equal to 1, and on 1 electron is encircling round the nucleus, and Z is equal to 2 for singly ionized helium atom, that is Ag plus. So for Ag plus, this is also 1 electron atom, but in this case of Ag plus, value of Z is 2. Similarly, if we consider the lithium atom, that is Li double plus, in that case Z is equal to 3, but it is 1 electron system. Such atoms are called hydrogenic atoms or hydrogen-like atoms. The charge on the nucleus is Zd, Z multiplied by E, and that on the electron is minus E. So the value of the Coulomb interaction, that is potential due to the Coulomb force, is given by Vr is equal to minus Z square by 4 pi epsilon 0 r. So from this mathematical expression, we can see that this potential depends on the distance r between the nucleus and the electron. Hence, such type of potential will be spherically symmetric. Now, if small m is the mass of the electron and capital M is the mass of the nucleus, then the reduced mass of the system is mu is equal to small m into capital M divided by small m plus capital M. Now, from this expression, we can see that the mass of the nucleus, that is capital M, that is very large compared to the electrons mass small m. So we can neglect the electron mass in the denominator. So ultimately that capital M from the numerator and denominator, that cancels out, and reduced mass mu is very close to the mass small m, that is electron mass. So with these approximations, we can say that we shall replace mu by small m. That is, we shall consider the nucleus to be stationary. We are considering nucleus is a stationary, that is why we can consider mu is very close to small m. The correction for the nuclear mass is then simply a matter of replacing small m by mu. So if we want to correct that, we have to replace small m by mu. Now we have already established the radial equation for the hydrogen atom. We can already establish the radial equation for the hydrogen atom. Now what we will do, we will just replace small m by mu. So let us see the structure again. We have deduced the radial equation in equation 12.12. That means this is the structure of the radial equation. You see it again. In this equation is in terms of small r only, no angular coordinates are there. So here what we will do, we will put the value of Vr. We have already established the value of Vr here, and we will put the value of Vr, but we will not write the value of mu, and we will replace mu in terms of small m. So ultimately, and the final expression of the radial equation, that will become like this. So this is the expression of the radial equation. So we have just written value of Vr here. This is the value of Vr. So this is the expression of the radial equation, and we are aiming to solve this equation. Now the point is that we are interested only in the energies associated with the relative motion. In the previous lecture, we have already described, that is why we are only interested with the relative motion. We may assume that we are working in the center of mass system. That means we are on the center of mass system. So that the energy for the center of mass system E capital R will be 0. And the total energy E, that will be equal to the E small r, that is that will concern only the relative motion. Further, we shall be interested only in the bound state solution, and therefore we shall consider E less than 0. Now, in order to solve this equation, we have to introduce two dimensionless variable so that this equation can be simplified. So, these dimensionless variables are, the first variable is rho. Rho is equal to minus 8m e by h card square to the power half into small r. This is the first variable, and another variable is lambda. Lambda is given by this jd square by 4 pi epsilon naught h card into minus m by 2e to the power half. So, that can be again written as z alpha minus mc square by 2e to the power half, where alpha is equal to e square by 4 pi epsilon naught h cut c is almost equal to the 1 by 137, and this alpha is known as the fine structure constant. So, with this replacement, the above equation can be simplified to a great extent, and this equation becomes like this: d square r by d rho square plus 2 by rho dr by d rho plus lambda by rho minus 1 by 4 minus L into L plus 1 by rho square r rho is equal to 0. So, this is the equation in simplified form. This is the equation, that means radial equation. Now, we have to solve this equation. So, how to solve? In order to solve this equation, we first examine the asymptotic behavior of r rho. Here function is r is a function of rho, and for rho tends to infinity, this equation reduces to d square r by d rho square minus 1 by 4 into r rho is equal to 0, because as rho tends to infinity, so 1 by rho tends to 0. So, as 1 by rho tends to 0, so writing 1 by rho is equal to 0 in this equation simplifies to this equation d square r by d rho square minus 1 by 4 into r rho is equal to 0. Now, the solution of this equation are proportional to e to the power plus minus rho by 2. It is easily can be predicted, that is the solution of such type of equation will be e to the power plus minus rho by 2. But out of these two solutions, only e to the power minus rho by 2 is acceptable. Why? Because e to the power rho by 2 becomes unbounded, that means it becomes infinity when rho tends to infinity. But e to the power minus rho by 2, that will not become infinity at the point rho tends to infinity. That is why e to the power minus rho by 2 is acceptable. This is asymptotic solution. Asymptotic solution means this is approximate solution. Now, if we consider the exact solution, then exact solution will be e to the power minus rho by 2 multiplied by a function which is a function of rho. So, we are saying that this is capital F. So, e to the power minus rho by 2 into capital F. Capital F is a function of rho. That will be the form of the exact solution of equation 12.31. That means for this equation. Now, if we substitute the value of r in equation 12.31, means this equation. So, after the substitution of the form of r in this way, if we substitute this equation in 12.31, then this equation will become, that is after some algebraic rearrangement, and this equation will become like this. This is given in equation 12.34. So, this is a second order differential equation. Now, you see that if we set rho is equal to 0, if we set rho is equal to 0 here, so second term will be 0 and first term will also be 0, and from the last term we can predict that L into L plus 1 into F0 is equal to 0 or F0 is equal to 0 for L not equal to 0, because as L is not equal to 0, so F0 is equal to 0. As F0 is equal to 0, we can say that the power series solution for f rho cannot contain a constant term. So, this equation can be solved in a series solution method. So, we can assume that f rho can be written as ak rho to the power s plus k. So, for the method of series solution, I recommend that you just suggest some standard mathematical physics textbook, and there you can find the method of series solution. So at first we have to assume f rho is equal to ak rho to the power s plus k. Then you have to find df by d rho. Then you have to find d square f by d rho square. Then you have to substitute these values in this equation. After the substitution, this equation will become like this. That means given by equation 12.37. This is the equation after substitution of the value f rho in this equation. Now, for this equation to be valid, the coefficient of each power of rho must vanish. Equating the coefficient of rho to the power 0 to 0 gives, if we set the coefficient of rho to the power 0 to 0, then this equation will become, that means here you have to set k is equal to 0, so that you can equate the coefficient rho to the power 0 to 0. So then from this expression we can say that is s into s plus 1 minus l into l plus 1 is equal to 0. If you have to set k is equal to 0 here, and the right hand side will be 0. So from this we can say that either s equal to l or s equal to minus of l plus 1. Now if we take s equal to minus of l plus 1, then the first term in the expansion 12.36 means here the first term in the expansion of 12.36, that will become a0 by rho to the power l plus 1, because you have taken s is equal to minus of l plus 1, and for first term k is equal to 0. So first term will be a0 by rho to the power l plus 1, which tends to infinity as rho tends to 0. So as it becomes infinity at rho tends to 0, so we cannot take s equal to minus of l plus 1, and we have to take s equal to l for physical acceptability. So s equal to l. Now setting the coefficient of rho to the power k plus 1 equal to 0 in this expression. So for rho to the power k plus 1, you have to set k is equal to k plus 1 in this coefficient, then you have to equate to 0 as per the rules of the series solution. So if you set the coefficient of rho to the power k plus 1 is equal to 0, then we can obtain this equation. And from this equation we can obtain a recurrence relation putting the value of s is equal to l, which was obtained earlier, that is s equal to l. So from this relation we can obtain a recurrence relation. I am again saying that is you can you have to see some standard textbook of mathematical physics for the method of series solution, then you can understand these steps very carefully. So this relation is known as the recurrence relation, ak plus 1, that can be expressed in terms of ak. This relation can give you the different values of the coefficients a1, a2, a3 in terms of a0. You see the left hand side. So suppose for k is equal to 0, then a1 can be expressed in terms of a0. If you take k is equal to 2 here, then a3 that can be expressed in terms of a2. Again a2 can be expressed as a1, a1 can be expressed as a0. So all the terms can be expressed in terms of a0. Now in order to infer about the behavior of the series 12.36 means this series, so what we can see that for very large values of k, if we set limit k tends to infinite, and ak plus 1 by ak, that will be 1 by k. How we can see this? Because you see this relation between ak plus 1 by ak, and you know the rules of the limit which we have learned in calculus. So if we write ak plus 1 by k, ak is equal to this one, and set the value of k tends to infinite, then we can easily show that limiting value of ak plus 1 by ak at k tends to infinity will be 1 by k. This is similar to the asymptotic behavior of the expansion of the function e to the power rho as shown below, because you see that e to the power rho is equal to k is equal to 0 to infinity ck multiplied by rho to the power k, where ck is equal to 1 by k factorial. That means any exponential series can be expressed in this format. This is the rule to expand an exponential series. We know that, we have already learned in Taylor's theorem. So ck is equal to 1 by k factorial. So e to the power rho can be expanded like this. Now again, if Ck is equal to this, that is 1 by k factorial, then we can say that is Ck plus 1 divided by Ck is equal to k factorial by k plus 1 factorial. Again it is equal to, if we take k plus 1 common from the numerator, so that will be k plus 1 into k factorial. So ultimately it will be 1 by k plus 1. And if we take the limiting value, that is if we set k is equal to infinite, so for k is equal to infinite, Ck plus 1 by Ck is equal to 1 by k, because you see when k will become infinite, then you can neglect plus 1 term. So it can be easily shown that this is 1 by k. Now what we have learned, you see that this exponential series that can be and for that series the value of Ck plus 1 by Ck for k tends to infinity is 1 by k. This is Ck, that is coefficient of rho to the power k, and again for this power series Ak plus 1 by Ak is equal to 1 by k. So these two series behave almost similarly. So if the series 12.36 does not terminate, then f rho will behave as e to the power rho. So f rho, that will behave as e to the power rho, because we have already established that their behavior is almost same. So if f rho behaves as e to the power rho, we can write that is r rho will behave as e to the power rho by 2. Why? Because you see that equation 12.33, let us see it again. You see r rho is equal to e to the power rho by 2 into f rho, but f rho behaves as e to the power rho. So r rho will behave e to the power minus rho by 2 into e to the power rho, that means e to the power rho by 2. So r rho will behave as e to the power rho by 2, but it diverges as rho tends to infinite. Since this is not acceptable, the series must terminate at some value of k, say nr. So how to terminate the series? We can terminate the series by observing the recurrence relation. You see that Ak plus 1 by Ak plus 1 by Ak is equal to this expression. Now how to terminate the series? Suppose for some values of k, that is equal to nr, if the right hand side is 0, if we write the left hand side as Ak plus 1 by Ak, and right hand side is this one, that is k plus l plus 1 minus lambda divided by this. So this can be made 0 when the numerator is 0. If the numerator is 0, then we can say that the term Ak plus 1 for a particular value of k is equal to suppose nr, that is become 0. So to terminate the series, we have to make somehow the numerator is equal to 0, and we are assuming the numerator is 0 for a value of k is equal to nr. That is why lambda will become from this relation, that is k, we are writing k is equal to nr. So nr plus l plus 1 minus lambda is equal to 0. So lambda will become nr plus l plus 1, that is we are writing here. So lambda is equal to nr plus l plus 1, and we are assuming lambda is equal to a positive integer, that is n is a positive integer. Now since both nr and l can be positive integers or 0, it is clear that n can have only positive integral values. So n can have only positive integral values. So here nr is called the radial quantum number and small n is called the principal quantum number. And for a given value of n, the allowed values of l are 1, 2 in this way, maximum up to n minus 1. So we have to keep in mind that the allowed values of l are 1, 2 in this way up to n minus 1. Now if lambda is equal to n, now from a relation given in equation 12.30, you see the equation 12.30 again, then you will understand it very clearly. You see, we have assumed a dimensional constant lambda is equal to this one, where lambda, now we have established that lambda is equal to small n. Now if we write n in the left hand side and if this is the right hand side, so in the right hand side there is energy term, so we can estimate the energy value from this equation. So now what is the energy value? The energy value is this one, En is equal to minus m by 2 h cut square into z square by 4 pi epsilon 0 to the power 2 1 by n square. This can be expressed in terms of alpha also, but whatever this equation, that is expression for the energy, is exactly same with that obtained from the Bohr model. In Bohr model we have obtained the similar expression of the energy, but Bohr model was based on ad hoc assumptions, but this energy expression has been derived from the quantum mechanical treatment. So it was the most important early success of the Schrodinger's theory, because it could reproduce Bohr's formula from a general equation of motion. So this is the success of the Schrodinger equation. Now it can be noted that the value of n may take all integral values from 1 to infinity. N takes the integral values. As such, the bound state energy spectrum of a system held by the Coulomb force contains an infinite number of discrete energy levels, and we know that for a bound state energy spectrum held by the Coulomb force, and that contain infinite number of discrete energy levels, because values of n are discrete and it is from 1 to infinity. This is because the magnitude of the Coulomb potential decreases slowly at larger smaller. On the other hand, short range forces have a finite number of bound states. So if the force is short range, then it has a finite number of bound states. Now what is degeneracy? A very important point to note is that energy eigenvalues depend only on the principal quantum number small n. There is no dependency on small l or ml. You see the expression again, you see in this expression En depends on n only. En does not depend on small n, small l or ml. On the other hand, the eigen functions for a hydrogen atom are determined by the values of the three quantum numbers n, l and ml. We have already read about the eigen function y, that is spherical harmonics. So that eigen function depends on all the three quantum numbers, that is n, l and ml. But the energy eigenvalue depends only on n. So for each energy level En given by this equation, there are more than one distinct states which have the same energy. That is, for more than one distinct states, the energy is same. This phenomena is known as degeneracy. That is, different states have same energy. More than one distinct states have same energy, and this phenomena is known as the degeneracy. The Bohr model was extremely inadequate because it did not account for the degeneracy, which was important consequence as we see later step by step. The degeneracy with respect to the quantum number ml is present for all spherically symmetric potential. The degeneracy with respect to the quantum number L is the characteristic of the 1 by r Coulomb potential. So the degeneracy with respect to the L comes from the 1 by r Coulomb potential dependence. Now let us find the total degeneracy of the energy level En. So how to find that? We know that for a given quantum number, principal quantum number n, the quantum number small l can take values starting from 0 to n minus 1. Again, for each value of l, the quantum number ml can take 12 plus 1 possible values. So the total degeneracy will be summation of 12 plus 1, where the range of L is 0 to n. So if we expand this summation form, so for first term, if we look at the first term, so that will be 2 into summation of L. So 2 into summation of L, that summation of L where range is 0 to n, that will give you 2 into n minus 1 by 2, and this is a constant term 1 only. So 1 into summation of L is equal to 0 to n, that will give you n only. So after adding, it will give you n square. So this is the value of the degeneracy, but we have to keep in mind that there is another property of electron, that is spin. It has a spin angular momentum that makes them fall in two possible states, one for the up spin and another for the down spin. So we have to multiply two states here, because for each of the states there are two spin states. So actual degeneracy is 2n square. So let us look at some of the energy levels of the hydrogen atom. So you see that for different values of L, we use different letters. For example, for value L is equal to 0, we use the symbol S. For L is equal to 1, we use the symbol P. For L is equal to 2, we use the symbol D in this fashion. These are spectroscopic notation. Now we know that for a particular value n is equal to 1, value of L will be 0 to n minus 1. So, for n equal to 1, L will be 0. This is one state. Again, for n equal to 2, value of L will be 0 and 1, because maximum value of L is n minus 1. So, for n is equal to 3, L will be 0, 1, 2, and the value of ml is 2L plus 1, and it starts from the minus L to plus L. For example, suppose value of L is 1. So, value of ml will be minus 1, 0 and plus 1. So, let us see some figure, then it will be clear. For example, suppose n is equal to 3. So, for n is equal to 3, L will be 0 and L will be 1 and L will be 2. Again, these states can be classified in this way. For L is equal to 0, there is no more subdivision. So, it is only 3 states. We are using 3 because n is equal to 3. 0 L equal to 0 means A state. That is why we are writing 3s. 3 means n equal to 3. So, for L equal to 1, value of ml will be plus 1, 0 and minus 1. So, 3 more states will be there, and for L equal to 1, we will say that P state 3 is given for n is equal to 3. For L is equal to 2, value of L will be starting from minus 2 to plus 2. That means minus 2, minus 1, 0, plus 1 and plus 2. And as L is equal to 2, we will say D states. 3D is for n is equal to 3. So, in this way we can divide different states for n is equal to 3. Now, we will again come back to the solution of the radial equation. We have started from equation 12.34. Let us look at it again. Equation 12.34. This equation, we have started from this equation, but we have not completely solved it yet. What we have done, we have shown that energy value depends on the value of principal quantum number n only, but we have not completely solved it. So, how to solve it? So, the above discussion suggests that we seek a solution of the form f rho is equal to rho to the power L into L rho, where L rho is a polynomial. So, if we assume the function f rho is like this, then we can solve this equation. So, now we have to substitute this format of f rho in equation 12.34, and if we put lambda is equal to n, which we have already established, then this equation will become like this. The physically acceptable solutions of this equation may be expressed in terms of the associated Legur polynomials, and this equation can be a little bit simplified if we express L rho in terms of the generating function u rho. So, if we use this generating function, so this equation will be ultimately simplified to this equation. We are not going to details of the method of solution, but what is our aim is to state that this equation can be simplified like this equation, and this equation is known as the associated Legur polynomial equation, where associated Legur polynomial is defined as L P Q rho is equal to dP by d rho P L Q rho. This is associated Legur polynomial. Now, we have to solve this equation by the typical method of the Legur polynomial equation, and for this I again suggest you to check some standard mathematical physics textbook. We are not going to detail method of the solution, but we can show that the solution of such types of equation can be expressed as in this way, that is, if we solve this equation, then the full radial eigenfunction will become r NLR is equal to capital N, that is a constant, e to the power minus rho by 2, rho to the power L, and L 12 plus 1 n plus 1 rho. This L is the associated Legur polynomial function, and RNLR is the radial eigenfunction. Capital N is a constant. This is a normalization constant, and we have already said the values of rho in the beginning of the differential solution of the differential equation. We have already stated the expression for the rho. So this is the expression for the rho. This can be simplified in this way, that is 2z by n a0 into r by putting the value of E. So the constant n can be determined by normalization condition. We already know that is how to normalize that. So after the normalization, the value of n, and so value of n will be like this. And if we ultimately calculate the exact expression of the RNLR, so this is the exact expression for the radial wave function. This is the exact expression given in equation 12.55. You see that there is some constant there, and this is exponential term multiplied by rho to the power L, and this is Legur polynomial function. This is the radial part. So what will be the complete part? Because you see, you can remind that in the beginning of the solution process of the differential equation, we have assumed that is psi r theta phi, and that was separated into two wave function. That is, first is the radial part RNLR, and the next one is the angular part YLM theta phi. Now the structure of the spherical harmonics Y, that we have already discussed in the lecture of orbital angular momentum, and this is the function of the, this is the radial wave function R, and here the value of n can be 1, 2, 3 in this way up to infinite. Value of L can be L 0, 1, 2 in this way up to n minus 1, and value of ML will be minus L to minus L plus 1 in this way up to L. That is, ML can take 12 plus 1 values. Now for different values of n, L and ML, we will obtain different form of the wave function. So what will be the different form? For example, suppose we have shown 3 radial eigenfunction. You see the suffix 1 0. So here NL. So 1 0 means n is equal to 1, L is equal to 0. So this is R10, this is R20, this is R21. In this way, we can express different radial eigenfunction which will depend on the values of n and L. And we can also plot this wave function. You see, if we plot this wave function graphically, so this is the x-axis is the distance smaller, and the y-axis is the value of this radial wave function. So you see, this is the plot of R10, this is the plot of R20, and this is the plot of R21. Now you see that here at r equal to 0, R10 is not 0, R20 is also not 0. Why? Because there is a term r to the power L in the expression of RNL. You see, in the expression of RNL, this is as rho to the power L. Rho to the power L means as rho depends on r, so this will be r to the power L also, and if L is equal to 0, then this will be 1. So in that case, RNL will be non-zero for small r is equal to 0. So this shows the non-zero values of RNL from the graph. But for R21, you see that at r equal to 0, R21 is 0. So these are the different graphical plots for the radial wave functions. And if you see the complete wave function, that means combining both radial and angular part, so the structure of the wave function will be like this. For example, this is psi 100, this is psi 200, etc. So this is the complete eigenfunction for the lowest few states. So we have discussed how to solve the Schrodinger equation for the hydrogenic atom, and we have established the complete expression of the eigenfunction. This is the complete expression of the eigenfunction psi NLM theta phi, where RNL is given by this one, and the expression of YNL phi we have already discussed in our lecture of orbital angular momentum. So I think we have understood the lecture. For further understanding, I will request you to go through the textbook of MC Jain. This lecture is from the textbook of MC Jain. So you can go through that textbook very carefully for further understanding. And thank you all for listening the lecture.